Hello everyone, I'm Hongjie Wang, an undergraduate research summer intern at Rice University under the supervision of Professor Ye Li. I'm excited to present our work, a new MRAM-based processing memory accelerator for efficient neural network training with floating point precision. For this presentation, I will first introduce the background and motivation, and then give an overview of our proposed PIM accelerator for training. After that, the computing methodology and the evaluation of our proposed accelerator will be described. Finally, a conclusion will be given to summarize our contributions. Nowadays, deep neural networks have widespread applications in various fields. However, recent breakthroughs of powerful DNNs rely on massive data and computational power, making DNN training very challenging. Firstly, DNN training causes prohibitive time cost. For example, training a medium-scale DNN ResNet 50 requires 14 days using a Media M40 GPU. What's more, DNN training has raised pressing environmental concerns. For example, the carbon emission of training a medium-scale DNN approximately equals to one car's lifetime carbon emission. Processing in memory has emerged as a promising architecture for DNN acceleration. And as the left figure shows, state-of-the-art PIM accelerators achieve higher energy efficiency and computational density compared to the newest GPU. The improvement results from two main reasons. One of them is the utilization of emerging non-volatile memory, such as MRAM and RRAM, to store a huge number of parameters. The emerging non-volatile memory has both high memory density and high access efficiency during computing. Another important reason is that PIM, as a new architecture, decreases costly data movements in von Neumann architecture. For example, the energy cost of data movement from DRAM could be 200 times as that of arithmetic logic units. By decreasing the costly data movement, we can perform DNN training with small computers. However, existing PIM accelerators have several drawbacks when accelerating DNN training. First of all, most of them support only inference with low precision computation. Secondly, due to the widely used RRAM-based implementation, writing in these accelerators is costly, which results in high energy consumption and latency during training. What's more, state-of-the-art digital PIM accelerators achieve only limited Boolean functions, resulting in high computational complexity. In order to solve these problems, we propose a new PIM accelerator, which supports both inference and training with floating point precision. Thanks to the adopted SOT MRAM-based implementation, we achieve the low writing current and thus low energy consumption and latency. What's more, due to plentiful available Boolean functions implemented in MRAM cells, we achieve more efficient computing compared to state-of-the-art works. Next, I will give an overview of our proposed accelerator. We designed our proposed accelerator featuring three innovations. Following the bottom-up order, firstly, we develop a 1T1R SOT MRAM memory cell, which favors more efficient and flexible read and write. Secondly, we propose a new full addition design that requires fewer read and write clock cycles to finish addition operations compared with state-of-the-art design. Thirdly, we develop efficient designs of dominant floating point addition and multiplication for digital PIM accelerators. Finally, we integrate all the aforementioned designs to demonstrate a new PIM-based DNN training accelerator. Then I will introduce our computing methodology for the proposed accelerator to you in detail. This is the proposed 1T1R memory cell. Why do we use the 1T1R structure? The existing two designs of the SOT MRAM cell are 2T1R and crossbar structure. For the 2T1R structure, the cells in one row can be controlled separately, resulting in a high flexibility when computing in the memory array. However, the 2T1R structure has a relatively low memory density due to the two extra transistors in one cell. The crossbar structure has a relatively high memory density by eliminating all the transistors. But for this structure, cells in one row cannot be controlled separately, leading to low flexibility and extra clock cycles when computing in the memory array. Is there a way to balance the flexibility and density better? Yes, our proposed 1T1R structure eliminates one transistor in the 2T1R structure, thus improves the memory density. Unlike the crossbar structure, cells in one row can be separately controlled for 1T1R structure. Thus, the high flexibility of 2T1R is kept. Note that eliminating one transistor will introduce leakage current in other cells, but it is much smaller than the write current and generates negligible extra power. Based on the 1-to-1 cell structure, how can we organize the data transfer between them to implement full addition? The 1-bit full addition is performed based on 3 logic functions implemented in the SOT-MRAM memory cell. The figure in the upper right corner shows the 3 logic functions and the definition of parameter A, B, and C. A and BI are 2 operands of logic functions. BI is stored in the cell before computation. C controls the type of function applied. After computation, the result BI plus 1 will be automatically stored in the cell. With the help of these functions, we implement full addition based on the 1-to-1 cell. In the first step, we copy 2 operands X and Y and the input carry Z to cache parallelly. In the second step, we parallelly perform the AND and XOR functions in 2 cells of cache respectively. In the third step, we copy the XOR result to an extra MRAM cell and perform the AND function in the third cell of cache parallelly. In the last step, we perform the XOR function in the extra MRAM cell and get the sum SR. And parallelly, we perform the OR function in the third cell of cache and get the output carry. Thus, we finished 1-bit full addition in 4 clock cycles of read and write. Compared with state-of-the-art work, our proposed method of 1-bit full addition reduces the number of required read and write clock cycles and extra memory cells by 69.2% and 80.0%, respectively. The improvement benefits from more available Boolean functions in the memory cell and thus reduced computational complexity. As shown in the formula, Mram Pim implements only 1 Boolean function, nor in the memory cell, leading to complex computation. Contrary to this, thanks to 3 Boolean functions implemented in the memory cell, our proposed method has much lower computational complexity. Based on the 1-bit full adder mentioned before, it is easy to implement multi-bit full addition. Then, how can we organize it to achieve the improved floating point computation design? For floating point addition, our key innovation is the implement of an operation called search. So what is search and how does it contribute to the improvement of computational parallelism? Let's consider part of the process of addition. Make the assumption that we are going to perform addition between AI and BI parallelly. These operands are stored in the memory as shown in the right figure. In order to perform addition between matrices, we need to align the exponents and right-shift corresponding matrices. The number of right-shifting bits is determined by the difference of exponents. Thus, we perform the subtraction between exponents of operands AI and BI parallelly, and we store the results exp prime and the exp double prime to corresponding columns. However, the exp prime and exp double prime have various values, and we cannot right-shift different matrices by different bits at the same time. Trivially, we need to perform right-shifting one by one. In order to parallelly perform right-shifting for those having the same exp prime and exp double prime, we propose a search method. When a certain number Q1 is inputted, columns storing the equivalent exp prime and exp double prime output match signal, and matrices in the corresponding columns will be parallelly right-shifted by Q1 bits. In another clock, another number Q2 is inputted. There are some other columns outputting match signal, and matrices in corresponding columns will be parallelly right-shifted by Q2 bits. How is the search method implemented? If all the bits in the same column match the input bits, the total output current in the source line of this column will be low. If you are interested in the details, you can easily find them in our paper. Apart from addition, how is the multiplication improved? For floating point multiplication, our key innovation is the utilization of target buffer in a pinpoint manner to maximize the buffer reuse while keeping the column-wise parallelism. Based on the design mentioned before, the XOR and addition in the floating point multiplication can be easily performed parallelly. For the fixed point multiplication between matrices, we use 2 target buffers working in a pinpoint manner for storing intermediate results. For each pair of matrices, we have 2 multiplication buffers in 2 different columns. In a certain clock, 1 bit in the matrice B, BI, is read and the writing target buffer is set as number 1. If BI equals to 0, we can just copy the intermediate result in the buffer number 0, right-shift it by 1 bit and store it in the writing target buffer. If BI equals to 1, we right-shift the intermediate result in the buffer number 0 by 1 bit, perform addition between it and Matisa A, and finally store the addition result in the writing target buffer. In the next clock, the next bit in the Matisa B, BI plus 1, is read, and the writing target buffer is set as number 0. We perform similar operations to that in the previous clock. And then in the clock after the next clock, the writing target buffer will be switched back to number 1. This above circulation will be repeated once and once again in the process of multiplication between Matisas. Note all the operations associated for different pairs of Matisas are performed parallelly. Compared with state-of-the-art work float Pim, for floating point addition, our proposed design reduces the required number of read and write clock cycles by 80.5% for 32-bit floating point numbers and reduces the complexity from n squared to n. Here n represents the bit width of each floating point number. For floating point multiplication, the required number of read and write clock cycles and memory cells are reduced by 81.1% and 77.4% respectively for 32-bit floating point numbers. In the following part, I will introduce the evaluation results of the proposed accelerator. Our evaluation setup is shown here. The evaluation is performed at 2 levels. One of them is the floating point computation level, and another is the DN training level. We incorporate the basic SLT Mram cell parameters as described in the document and a recent current sense amplifier into MVC, a dedicated simulator for emerging non-volatile memory arrays. With the help of MVC, we can get the memory array area and the latency and energy cost per read and write from the memory arrays, following the array configuration of float Pim. We further implement a dedicated Pim accelerator simulator to evaluate the total area, latency, and energy required for training. We compare the proposed accelerator with state-of-the-art digital Pim accelerator float Pim to illustrate the superiority of our design, and the training evaluation is based on the 95 model and the MList dataset. For 32-bit floating point numbers, the evaluation result shows that compared with float Pim, we improve the latency efficiency by 1.8 times and the energy efficiency by 3.3 times when performing the same computation MAC in the same size of memory array. The improvement benefits from the fewer required read and write clock cycles due to improved full addition and floating point computation design. It also benefits from the fact that compared with RRAM in float Pim, the adopted SOTM RAM requires a lower write current and thus a lower energy cost and latency for pre-charge when writing memory arrays. When performing training for the model of 95 based on MList dataset compared with float Pim, the proposed accelerator improves the area efficiency, latency efficiency, and energy efficiency by 2.5 times, 1.8 times, and 3.3 times respectively. This improved performance is resulted from 2 facts. One is that the fewer cells required to store intermediate results due to the improved full addition and the floating point computation design. Another is that the proposed accelerator has a higher design flexibility. Unlike float Pim, which requires the operands, intermediate results, and the final result to be stored in the same row when performing computation, memory cells at different rows and columns in the proposed accelerator can be used to store intermediate results flexibly, which maximizes cell reuse opportunities. Note that the improvement of the proposed accelerator's energy efficiency and latency over float Pim is similar to that of a MAC, because energy consumption and latency of MAC dominates that of training the small model, the Net5. Finally, I would like to make a summary of our paper. We propose a new SOTM RAM-based processing memory accelerator for efficient training with floating point precision. Specifically, following the bottom-up order, we integrate the proposed new design of memory cell for addition and floating point computation to demonstrate it with high efficiency. The evaluation results show the superiority of the proposed accelerator over state-of-the-art works in terms of energy, latency, and area efficiency. Thanks for your listening.